Okay, so let's move to lecture 3, diffusion equation and its corresponding solutions. Why we need to know how to get its corresponding solutions? Because as we know, diffusion equation is what we learn here, right? It's a partial C, partial T. How the concentration of your interesting atoms changes with time can be expressed like a minus flux divergence of the flux. But however, the flux is not easy. It's not easy to measure the atomic flux. So we want to convert this flux as a measurable factor or parameters. So from here to here, we use the fixed first law is a minus diffusivity concentration gradient. So instead of using the flux, we convert it to a gradient, concentration gradient, and concentration gradient is easy to measure. It's a measurable of physical intensities. So the reason we want to have a diffusion equation and want to solve the solution because we want the flux is not easy to measure, but it will be easy to measure the concentration of the diffusing atoms. So as long as you solve this diffusion equation, then you can get the C as a function of location X and T, right? So that's why we need to know how to solve that and get the corresponding solutions. And besides this, as you learn, lecture 2, we introduce like several driving force can cause a mass transport. And also lecture 3 tell you how to get the concentration of this diffusing atoms as a function of X location and time. But it's a little bit a missing piece between this mass transport and entropy production rate, right? So I give you a quick review. In order to, this is kinetics, right? So if you think about what we learned in lecture 1 would be, usually in any kinetics process, you can use the entropy production rate to describe how fast this kinetics process, right? So we use the entropy production rate. So if we want to use entropy production rate to describe diffusing in solid materials, then based on the flux driving force equation we learned in lecture 1, then you can use a temperature times the entropy production rate equal to flux, atomic flux times the driving force, right? Driving force here in the mass transport is a minus chemical potential gradient. It's this term, so the atomic flux can be written as a mobility, concentration, and driving force, and times the driving force. So you got the mobility, concentration, and driving chemical potential gradient square, right? So by using this, you can also successfully to use the entropy production rate to describe the diffusion phenomenon. And this is chemical potential gradient. Is it easy? Is it easy to measure? No. As the flux is not easy to measure, and so does the chemical potential gradient. So use the Einstein relationship we demonstrate to you in lecture 2. You can get the entropy production rate. You can just substitute the chemical potential gradient you can just you can substitute this term as a concentration gradient by using an instant relationship, and then you got this equation, right? This relationship. So the entropy production rate is associated with concentration gradient squared. So if the concentration gradient increase, that tell you the entropy production rate increase in the meantime. So as long as you get the concentration profile and take the gradient, then you can get the entropy production rate to well describe how fast this diffusing happen. Okay. So in this, so this is just give you some idea. Try to link the diffusion with entropy production rate. Okay, so in lecture, let's back to lecture 3. Lecture 3 actually divided in 4 parts. The first one is we are going to show you the diffusion equation, not only in mass transport, and also for heat and charge transport. And in the second part, as long as you formulate the diffusion equation, the next you need to know the boundary condition or the situation, boundary condition of your material or of your system. Is it a steady state or non-steady state? So what's the boundary condition? The steady state means if we talk about the mass transport in solids, so will be the concentration do not change with time, but there exists a concentration gradient. We call it a steady state flow process or mass transport process. Non-steady state means the concentration of diffusing atom changes with time, and also definitely exists a concentration gradient along your materials. And under these 2 different boundary conditions, then you can get the corresponding solutions to get how the concentration of diffusing atom changes with location and time. And in the third part, we are going to tell you the real cases. Usually the diffusivity is not a constant. Usually the diffusivity is changed with concentration of diffusing atoms. So how to calculate the diffusivity? And we are going to show you analyze, which people call it as a Boltzmann-Montanaro analyze, to get how the diffusivity change with concentration of diffusing atoms. And the last section of this part would be the diffusivity. Yes, diffusivity will be changed with concentration of the diffusing atoms, and also diffusivity will be changes with crystal structures. So we are going to show you what's the relationship between the crystal symmetry, asymmetry, and the diffusivity. How the crystal symmetry affects the diffusivity will be the last section in lecture 3. So let's move to the first part, is how to formulate the diffusion equation. How can you get or derive the diffusion equation you're familiar with? So everything is starting from the continuity equation. The continuity equation can be applied for not only for the mass transport, or also the heat conduction and the charge transport. So based on how can we derive the diffusion equation we're familiar with? Is starting from the continuity equation. As we mentioned before, if this is about the system we are interested in, is a system, a material system we are interested in. So based on continuity equation is the the concentration changes within this material will be equals to what? Will be equals to the generation of the mass per unit volume, the generation rate of this diffusing atom, right? Generate. And also how much the surrounding gives to this systems. How much flux, atomic flux get in to these materials. So will be the generation and plus the atomic flux from surroundings. So this is we call the continuity equation. So the generation plus given from the surroundings then equals to the total changes of the concentration in these materials. So this we call it a continuity equation. And so this N dot is either a generation or depletion of the atoms in these systems. So usually we will assume there's no source and sink operated into these materials. So the N dot will be equals to 0. So if you drop this term out because this equals to 0, so the continuity equation can be expressed like the partial C partial T equals minus the flux gradient. And based on Fick's first law, the flux can be expressed like the minus diffusivity concentration gradient. So that's you get the famous equation is we call the Fick's second law or diffusion equation, right? And next we need to make the other assumption is we call if we assume the D diffusivity is constant, then you can take this D out. So we got this famous is a partial C partial T diffusivity Laplacian operator on concentration. This is a diffusion equation you're familiar with, right? So how to derive the diffusion equation is starting from the continuity equation, right? Okay, so the same idea can be applied not only for mass transport, okay, also the heat transport and the electric transport. So we just change this here. We use a concentration, right? So if we talk about the heat transport, yes, the heat changes. Partial T is equal. Also, we assume there's no generation or depletion of the heat in your systems. So minus flux, the heat flux, divergence of the heat flux. And for the electrical transport, you just substitute the charge. Substitute the partial Q, partial T, and here you use the current density to substitute the heat flux. So you got this for electrical transport. So let's talk about the heat transport first. This is the partial Q, partial T, and the divergence of the heat flow, right? So if we take a look, it's similar, right? So let's we try to get the diffusion equation for heat transport, but the flux is hard to measure. So we want to try to do some we want to convert the flux and the heat to other measurable parameters or measurable material properties. So the heat can be dq is a Cp dt, right? Is a heat capacity times the dt. You got the heat, right? But the unit for here, Cp dt, is what? Is the joule per kg. As you know, in kinetics, people want to use per volume as a unit. It's easy to compare with other systems. So we use the unit volume. So you times the density, then you got the per volume. And the flux, based on Fourier's law, you got the minus kappa temperature gradient. So after arrangement here, you just use the density. You move the density and heat capacity to the right-handed side, and you got this. You can have a look here. What you have here is a partial T. T temperature is easy to measure, right? And the gradient, temperature gradient, and kappa is the thermal conductivity, density, and heat capacity. So, and you take a gradient on this term. So this is quite similar with diffusion, mass transport in materials, right? So some people also call this kappa divided by the density and heat capacity as a thermal diffusivity. Some people call this as a thermal diffusivity. Due to, if you compare with this one, D is a diffusivity, right? It's similar, right? It's a partial, just substitute is a T, and here is C, and this is T, just C, and diffusivity, so it's quite similar. So some people also call it this thermal diffusivity. As long as you solve this diffusion equation for heat transport, you can get the temperature, how the temperature changes with location and time. So temperature is a measurable parameters in your material systems. And if you use a constant concept to check the electrical transport part, yes. Current density is measurable, but Q here, how to convert is Q? So you use the capacitance, and d phi is the electrical potential, and current density use the Ohm's law. Then you just simply move the capacitance to the right-handed side, you got this one. So as long as you solve this equation, then you can get how the electrical potential changes with location and temperature. And electrical potential is a measurable parameter, right, in your material system. Okay, and so we already finished tell you how to formulate the diffusion equation, not only for mass transport, for heat, and also the electrical transport. And by the way, some people, probably you learn a Laplace equation before, right? And what's a Laplace equation? Some people would say, oh, Laplace equation is you put the Laplace operator on phi electrical potential and got it 0. So, but this is a Laplace equation. But what this means, I give you the other just explanation for this one. You can think about if this Laplace operator on the phi equals to 0, that means this equals to 0. So that means what? The electrical potential of the first thing is the flux definitely, because this is 0, right? So the flux current density here is current density equals to constant. So how much current in this material is how much equals to how much current out of this system. So the flux is constant, first thing, and also the electrical potential do not change, because this equals to 0, do not change with time. The same thing happened here. If you say, oh, Laplace, how about Laplace? This is our equation. But if you use the same concept here, if this equals to 0, that tell you it's a Laplace operator on temperature, right? So first thing you got is the flux, heat flux is constant. How much heat flux in equals to how much heat flow out. There's no heat accumulation in this system. This is the first thing you got. And the second thing is, let's do exist a heat flow. So that means there's a variation. There's definitely a temperature gradient or temperature variation exists in your system, right? But this temperature profile do not change with time. Okay, and for this case is the same thing, right? The current density, there's no current or there's no charges accumulate in your material, because how much current flow in equals to how much current flow out. There's no charge accumulation in this system. So so this is the physical meaning for Laplace equation, like you take equals to 0 is there's no charge accumulation in this material system. And there's a current, so definitely there's a variation of electrical potential, okay? But this profile, there exists a electrical potential variation, right? But this variation do not change with time because this equals to 0, okay? So let's move to the second sections, steady and non-steady solutions. In these sections, you need to figure out the boundary conditions in your material systems, or in your in your materials when the diffusion happens. So, and they are simply classified as two categories. The first one is we call steady state. The second one is non-steady state. Steady state means the concentration profile does not change with time. So, and non-steady state means the concentration profile of the diffusing species does change with time. So how to determine what kind of situation in your material systems, or in your when diffusion happens, how to determine? And as we mentioned before, the concentration profile, you can measure that, right? So you can measure the concentration profile along your material or in your materials at different time points. Then you can check whether the concentration profile does change with time. If it does not change with time, then in this case, in your experiments, it belongs to steady state. And if the concentration profile does change with time, then this material system belongs to non-steady state. And in this case, in order to get the full picture of how concentration profile does change over time, then you need to solve this diffusion equation. You need to get the corresponding solutions. So let's take then I give you an example. If this is a dialysis tube, and when we measure, because we can easily measure the concentration of diffusing atoms or molecules, right? So when I measure the concentration profile in this dialysis tube, then I can easily plot these curves. At the left-handed, the concentration keep at C0 for a very long time, and on the right-handed of this dialysis tube, and the concentration profile keep at CL for a very long time. And also in between, inside this dialysis tube, I find after measure the concentrations profile at different time points, I got these curves. So this curve, first things is I find that the concentration profile does not change with time. So I can determine in this situation or in this experiment, it is a steady state conditions. And next, I want to show you or demonstrate that the flux in this kind of situation, what's the flux? What's the value of flux, atomic flux in this case? So based on the diffusion equations, because the concentration profile do not change with time, this equals to 0. So I can simply confirm that the Laplacian operator apply on C, and if this is constant and this equals to 0, so the Laplace operator apply on concentration definitely equals to 0. This is a Laplace equation of concentration. And the flux, in order to get the value and magnitude of atomic flux, then we can flux equals to minus diffusivity concentration gradient based on the fixed first law, right? And this is the data I measured from my experiments. So based on this, I analyze. By analyzing these curves, then I can get the concentration profile as a function, as location, and express like this. Because this is a linear, so I can write down the ax plus b, and when x equals to 0, then concentration equals to C0, so I got B equals to C0. And also this slope, I can easily get that and substitute the A, right? So I can easily get the concentration profile. And in order to know the flux, so how to get the flux? Yes, you just partial with x, then times the minus diffusivity. Then, so just partial with this one, then you got this one, right? Because CL minus C0. And this is negative, so it becomes to C0 minus CL divided by L. Then you can so this I can get the C0 from my experiments, the data or I measure from experiments. I can get this, and this, so I can quantitatively calculate the atomic flux in my experiments. So when you have questions, or when you want to apply on your experiments, you need you need to measure the concentration profile at different time points. Then you can determine whether in this case it belongs to steady state or non-steady state. But yeah, this is much easier questions. Because it belongs to steady state. But however, when you got the concentration profile, if your concentration profiles does change with time, that means probably, for example, that you measure the concentration profile at 3 different time points, then you got 3 different curves that tell you the concentration the concentration of diffusing atoms changes with time, right? So that tell you it belongs to non-steady state. So because it is non-steady state, so the partial C partial T is not equals to 0. So at this point, you need to solve this partial differentiation equation. Then you can get a full picture. I mean, you can have a full picture of this concentration profile, how this concentration profile changes with location and time. So first, so as long as you confirm that in your case, the case belongs to non-steady state, so you can go through this the following steps to have a concentration profile. How the concentration profile changes with location and time by dealing with partial differentiation equation. Okay, so normally we were starting from you need to determine what kind of material system we are dealing with, and find out, because in this case, if we deal with diffusion phenomenon or mass transport in your materials, you need to determine how many driving forces involved in this diffusion process, mass flux. Then you can formulate the diffusion equation, and based on the suitable initial and boundary condition, then we can gather corresponding solutions to know how the concentration of diffusing atoms change with time and location. So next, in the following slide, we're going to show you there are 3 different cases. How to solve, how to identify. We are going to show you 3 different cases in belongs to non-steady state, and these 3 cases is commonly happens in your experiments. The first case is we call a diffusion couple. Diffusion couple usually is you have A bind with B, then you have diffusion couple. This diffusion phenomena is also unsteady state. And second cases would be the surface concentration decrease. I mean the limited source cases. A case with limited source. That means this diffusion process is for example, like you have silicon substrate. On the top of silicon substrate, you deposit like 1 nanometer thick, only one, very thin, 1 nanometer thick, constant. And this is limited. Diffusing atoms is going to, then you heat this up, heat this substrate up, then this limited diffusing atoms is going to diffuse from the surface, like one nanometer thick into the substrate. So this is we call a limited source, diffusing source. And the third cases would be we call it unlimited source. And this case, the characteristic for these cases is the surface concentration of diffusing atoms is fixed. For example, like you want to carbonize your parts, your metal parts, and you by flowing the methane, serving as a diffusing source. And because you continue supply the methane, so the surface concentration of the methane on your parts is fixed, and also you continue flow the methane, right? So it will be an unlimited source. So we are going to show you these 3 different commonly cases, and how to get the corresponding solutions for these 3 cases. Okay, so today we ended here.